Okay, previously we have talked about different atomic series prior to the quantum mechanical model. Weaknesses in series and models provide opportunities for science to improve. So today, let's have a look at the next two sections, the quantum mechanical model of the atom and quantum numbers. It's impossible to devise a perfect theory or model the first time around. Instead, science usually involves years and years of revisions and new discoveries. Science is constantly changing by identifying and improving on weaknesses. The successes of the Bohr atomic model was important because it showed that electrons exist in the discrete energy levels. Also, it explained experimental observations of line spectra in terms of quantum theory. But there were weaknesses in this model that other scientists identified, which paved the way for the complete development of the quantum model of the atom. By the mid-1920s, it had become apparent that Bohr model could not explain and make predictions about multi-electron atoms. A new approach was needed. Three physicists were at the forefront of this effort: Erwin Schrödinger, Louis de Broglie, and Werner Heisenberg. The approach they developed to explain properties of matter is called wave mechanics, or more commonly quantum mechanics. Louis de Broglie, a French physicist, originated the idea that the electron, previously considered just a particle, has wave properties. Pursuing this line of reasoning, Erwin Schrödinger, an Austrian physicist, decided to approach the problem of atomic structure by focusing on the wave properties of the electron. To Schrödinger and Broglie, an electron bound to a nucleus in an atom resembled a standing wave. So they began research on the description of the atom based on wave behavior instead of particle behavior. The strings on instruments such as guitars and violins are attached at both ends. When you pluck the string, it vibrates and produces a musical tone. The waves produced by the plucking are standing waves. They are called standing because they appear to be stationary. The motion of the string are a combination of simple waves of type shown here in Figure 1. So the black dots in Figure 1 represent the node, or points of zero lateral or sideways displacement for a given wave. Between two nodes, at the point where the amplitude of the wave is at its maximum, is the antinode. Note that there are limitations on the allowed wavelengths for the standing wave. Each end of the string is fixed, so there is always a node at each end. This means that there must be a whole number of half wavelengths in any of the allowed motions of the string. Here, Figure 2 shows standing waves can be produced by a wave generator. So this wave generator is said to produce standing waves that are 2 half wavelengths long. Schrödinger and de Broglie took the idea of standing waves and applied it to the electron in hydrogen atom. In their model, the electron is a circular standing wave around the nucleus, which is shown here in Figure 3. This circular standing wave consists of wavelengths that are multiples of whole numbers. For example, n could be equals to 1, 2, 3, and 4, and so on. Only certain circular orbits have a circumstance into which a whole number of wavelengths can fit. Any other orbits of the standing electron waves are not allowed because it could cause the standing wave to cancel out or collapse. That is, undergo destructive interference, which is shown here in figure 3c. This model seems like a possible explanation for the observed quantization of the hydrogen atom. The whole number multiples of wavelengths corresponds to the multiple fixed quanta of energy that the electron can have in the hydrogen atom. And however, the new question that this model raised was this: where is the electron located in the hydrogen atom? Okay, next let's have a look at two related concepts: orbitals and probability distribution. So Schrödinger's work on quantum mechanics led to his development of mathematical equation called the Schrödinger wave equation, and could be used to calculate electron energy levels. If an electron has a definable energy, then it can be localized in an orbital, which is a region around the nucleus where there is a high probability of finding an electron. But how can you locate something as small as an electron? Werner Heisenberg, who studied with Bohr, came up with a statistical approach for locating electrons. To measure the location and the speed of an object, you must be able to observe it. Life-size objects are easy to locate because you can see them, right? You can determine both the speed and the location of a moving car using a radar gun and GPS unit. For atomic-sized particles and smaller, any attempt to probe them changes their position, direction of travel, or both. This idea formed the basis of Heisenberg's uncertainty principle. Heisenberg demonstrated using mathematics that there are limits to knowing both where a subatomic particle is and its speed at a given time. According to Heisenberg's uncertainty principle, it's therefore impossible to simultaneously know the exact position and the speed of an electron. The best we can do is to describe the probability of finding an electron in a specific location. An electron orbital is analogous to students at a school moving from classroom to classroom during a scheduled break. The students are like electrons, the school is like an atom, and the classrooms are like orbitals. Someone who does not know a student's exact schedule may be able to determine the probability of that student being in a particular classroom at a particular time, but it's not certain. Another analogy with more appropriate relative sizes is a bee in a closed stadium. You know that the bee is inside the stadium, and you can reason that it will most likely be near its nest. However, you cannot pinpoint its exact location. So, a wave function is a mathematical description of an orbital in an atom where an electron of a certain energy is likely to be found. Note that a orbital is not a Bohr orbit. The electron is not moving around the nucleus in a circle. How then is the electron moving? The answer is surprising. We don't know that. The wave function gives no information about the detailed pathway of the electron. This idea is somewhat disturbing. When we solve problems involving the motions of objects in macroscopic world, we are able to predict their pathways. For example, when two billiard balls with known velocity collide, we can then predict their motions after the collision, right? However, we cannot predict the electron's motion. It's a mystery what electrons do in the atom, in the macroscopic world. Quantum mechanics does not describe how an electron moves or even if it moves. It only tells us that the statistical probability of finding an electron in a given location in the atom. The area of region where we are likely to find an electron is called an orbital. So using wave functions, physicists have created a three-dimensional electron probability density, which is a plot that indicates regions around the nucleus with the greatest probability of finding an electron. The electron probability density plot for a hydrogen electron in the ground state, or lowest energy state, is spherical and is called the 1s orbital, which is shown here in figure 4a. The greatest probability of finding the electron occurs at a distance r max from the nucleus, which is shown here in figure 4b. This distance is the same as the distance Bohr calculated for the radius of the first circular orbit of hydrogen's electron. So here, figure 5 illustrates the different electron orbitals or clouds. The electron can jump to any of these orbitals if it observes sufficient quanta of energy. Furthermore, these orbitals overlap rather than being distinct levels, as in the Bohr model. So we will learn this in more detail in the next few sections. The two main ideas of the quantum mechanical model of the atom are that electrons can be in different orbitals by observing or emitting quanta of energy, and that the location of electrons is given by a probability distribution. The quantum mechanical model is a radical departure from earlier atomic models because it's based on uncertainty, the uncertainty of an electron's location within the atom. According to this model, the structure of a tiny atom is much more complex than anyone would have thought possible. So we will have a look at this in detail in the next few sections. Okay, next let's have a look at the concept of quantum numbers. Mathematical equations are the language of scientists as they try to model natural phenomena. Schrödinger's wave equation is a very complex equation. It describes the quantized energies of the electrons in the atom as well as wave functions that determine the probability of finding electrons in various regions in the atom. So in the second half of this lesson, we will explore the results of Schrödinger's equation. So there are 4 different quantum numbers. Solutions to Schrödinger's equation for the hydrogen atom give many wave functions that describe various types of orbitals. Each of these types of orbitals have a set of 4 numbers called quantum numbers, which describe various properties of the orbital. These numbers are like addresses for locating the position of an electron by its city, street number, and apartment number. So, in the second half of today's lesson, we will learn about the 4 quantum numbers and what each quantum number represents. Okay, the first number is called the principal quantum number, which is denoted by letter N. Energy levels in an atom are sometimes called shells. Bohr devised this numbering system and called the shell number the principal quantum number. The principal quantum number N is a quantum number that describes the size and energy of an atom orbital. It has whole numbers. The values could be, for example, 1, 2, 3, and so on. It's important to note that the spaces between atomic shells are not equal, which is shown here in figure 1. So as N increases, the energy required for an electron to occupy that orbital also increases. Each successive orbital is larger, meaning that the electron occupying that orbital spends more time farther from the nucleus. This also means that electrons with higher energy are less tightly bound to the nucleus. So in summary, the principal quantum number N represents the position of an electron in the atom. If an electron moves from a higher shell, such as n equals 5, to a lower shell, such as n equals 1, the energy difference between the shells is released as a photon. Recall that Bohr took up the challenge of explaining the line spectrum of the hydrogen atom. Bohr's success led other scientists to pursue the investigation of line spectra in detail because there were observations that still required explanation. In 1891, Albert Michelson discovered that distinct lines in the hydrogen atom spectrals actually consist of many smaller lines. These smaller lines were difficult to see and were unexplained for many years. In 1915, a German physicist, Arnold Sommerfeld, studied the hydrogen atom spectrum in detail. To explain the actual lines, Sommerfeld proposed a secondary quantum number as a way to describe electron energy sublevels, or subshells, which are orbitals of different shapes and energies, as given by the secondary quantum number. The secondary quantum number, and it's often referred as S, P, D, and F. So subshells are part of the primary energy level. If an energy level is described as a staircase, one regular step actually represents a group of several smaller energy steps. And this concept is shown here in figures 2. The secondary quantum number, which is usually denoted by letter L. Secondary quantum number L describes the shape of an atomic orbital. It has whole number values ranging from 0 to n minus 1 for each value of n. This quantum number also describes energy of atomic orbitals. When n equals 1, L equals 0. When n equals 3, L could be the values of 0, 1, and 0, 1, and 2. Numbers used to describe L are usually replaced by letters to avoid confusion with n. So these letters are given in table 1 here. For example, as L equals 0, 1, 2, 3, 4, we use the corresponding letter to replace the numbers. These letters such as S, P, D, F, and G when L equals 0 to 4. In other words, at a energy level n equals 1, only a s orbital exists. However, at the third energy level, when n equals 3, there can be s, p, and d orbitals. Each of these orbital type is a subshell. Higher energy subshell symbols follow the alphabet, such as G, H, I, and etc. But no stable element in its ground state has electrons in subshells higher than F. This system of using letters to identify the various subshells arises from early spectral studies. Compared to different values of n, different values of L represent smaller differences in the amount of energy an electron requires to occupy any of the orbitals. Okay, next let's have a look at the third quantum number. The magnetic quantum number, which is denoted by ML. This is a quantum number that describes the orientation of an atom orbital in space relative to the other orbitals in the atom. It has whole number values between plus L and minus L, including 0. The values of ML is related to the orientation of an orbital in space relative to the other orbitals in the atom. The number of different values that ML can have equals the number of orbitals that are possible. So for example, when L equals 1, there are three possible orbitals: +1, 0, and -1, which is shown here in table 2. These three types of orbitals are all p orbitals, but they differ from each other by their orientation in space. For example, if you think of a xyz coordinate system in the three-dimensional space, the magnetic quantum number describes an orbital's orientation in the three-dimensional space. And here figure 4 shows the relative energies of the s, p, and d orbitals in their respective energy levels. So according to this graph, we can see that the energies of orbitals relative to each other, the farther the orbitals are from the nucleus, the closer together they are, and the subshells may overlap. Okay, next let's have a look at the shapes and orientations of the orbitals. We have learned that orbitals represent electron probability distribution, and that each orbital has a unique probability distribution, shape, and orientation, right? Note that the 2s and 3s orbitals contain areas of high probability separated by areas of zero probability, which is shown here in figure 5a on the top. So these areas of zero probability are called nodes. For simplicity, we can think of s orbitals in terms of their overall spherical shape, which becomes larger as the value of n increases. So on the bottom of figure 5a, we can see the characteristic spherical shape of each of the s orbitals. The p orbitals are not spherical like s orbitals, but have two lobes separated by a node at the nucleus. This is illustrated in figure 5b. The p orbitals can exist in any of the three dimensions and are labeled using the x, y, z coordinate systems, along with the lobes lie. For example, the 2p orbital with its lobes centered along the x-axis is the 2px orbital. And on the top right, it can be seen from figure 6 how the 2px orbital is identified using the first three quantum numbers. The 2 here is shell number, p is subshell number, and x here is a ml value, which is orientation in the space. The 3p orbitals have the same boundary surface shapes shown in figure 5b, except that they are larger because the value of n is greater. The d orbitals, well, L equals 2, first occur in level n equals 3. The 5 3D orbitals have the shapes shown here in figure 5b as well. 4 of the orbitals, namely dx, d, dyz, dxy, and dx squared minus y squared have four lobes centered in the plane indicated in the orbital label. Note that dxy and dx squared minus y squared are both centered in the xy plane. But the lobes of dx squared minus y squared lie along the x and y axis, whereas the lobes of dxy lies between the axes. The fifth orbital, dz squared, has a unique shape with two lobes along the z-axis and a belt centered in the xy plane. The d orbital for levels n larger than 3 look like the 3D orbitals, but again have larger lobes. And then we come to the last quantum number, which is called the spin quantum number, and usually denoted by ms. Samuel Goudsmit and George Anlebeck, graduate students at the Students of Leiden in Netherlands, found that a fourth quantum number, in addition to NL and ML, was necessary to account for the details of the emission spectra of items. Spectral data indicated that the item has a magnetic property called a magnetic moment. When the atom is placed in an external magnetic field, the magnetic moment of the item has two orientations. Since he knew from classical physics that the spinning charge produces magnetic moment, it seemed that reasonable to assume that the electron could have two oppositely directed spin states. This concept is illustrated here in Figure 7. The new quantum number related to the spin of an electron, called the electron spin quantum number, ms. This number can have one of two values, either positive 1/2 or negative 1/2. These two values mean that the electron can spin in one of two opposite directions, although other interpretations have been suggested. Okay, so that's the four different types of quantum numbers. And further, the Austrian physicist Wolfgang Pauli formulated an important principle called Pauli exclusion principle, which states the following. In a given item, no two electrons can have the same set of four quantum numbers, namely N, L, ML, and MS. Since electrons in the same orbital have the same values of N, L, and ML, the Pauli exclusion principle implies that they must have different spin quantum numbers, ms. Since only two values of ms are allowed, an orbital can hold only two electrons, right? Which must have opposite spins. This principle will have important implications when we apply the quantum mechanical item model to account for electron arrangements of the items in the periodic table. Okay, next let's have a look at a tutorial related to the quantum numbers we have learned so far. So consider this question here. For principal quantum number n equals 5, determine the value or values of the secondary quantum number L and the types of orbitals in each case. So I'll give you some time to consider this question by yourself, and then we'll have a look at the solution together, okay? let's have a look at the solution together. So for n equals 5, the allowed values of L are 0 to n minus 1, or 0, 1, 2, 3, and 4, right? The types of orbitals in each case are shown here in table 3. Remember, we need to use letters to replace the 0, 1, 2, 3, and 4. So the orbitals are 5s, 5p, 5d, 5f, and 5g. Any questions? Okay, if no questions, let's have a look at another one. Sample problem 2. How many possible values of ml are there for L equals 0, 1, 2, and 3? And can you spot any patterns in these numbers? And again, I'll give you some time to think about this by yourself, and after that we'll have a look at the solution together, okay? Alright, let's have a look at the solution together. So the principal quantum number n determines the values of the secondary quantum number, right? Which in turn determines the possible values of the third quantum number, or the magnetic quantum number ml. The magnetic quantum number ml is equal to whole numbers ranging from positive L to negative L. So for L equals 0, 1, 2, and 3, the values of ml are listed in table 4 as follows. When L equals 0, ml can be 0 only. When L equals 1, ml could be positive 1, 0, and negative 1. When L equals 2, ml could be positive 2, positive 1, 0, negative 1, and negative 2. And when L is 3, ml could be positive 3, 2, 1, 0, and negative 1, negative 2, and negative 3. Did you get it? Okay, so this is end of lesson C3L2, and I hope you learned something today. I'll see you next time. Bye.